Yeah. Good morning, everyone. All right, we start and midterm will not be joining us. So, okay, and last time we started a discussion about mathematical complexity. Okay, I hope that you all remember what we did. But today we want to speak about the covering number. Covering number that is a tool in order to bound the mathematical complexity of a given set. Okay, so I'm going to give the motivation behind the covering number, and then we start defining with different example, and then we finish with giving the bound of mathematical complexity in function of the covering number. So that's what we want to discuss. So, yeah, can you hear me?
Yes, I can hear you. You can go ahead.
All right. So, let me first make a reminder about the definition of mathematical complexity. Let's be a set, and we define the mathematical complexity of a set as 1 over m of the expectation over sigma of the supremum of the inner product of sigma and a. And okay, so last time sigma here, sigma I, sigma f, which take value in -1 over m. So that's how we define the mathematical complexity last time. And we saw an important theorem that's called Massac lemma that help us to give the generation bound of some SDM, some example that we did. So let me recall. Massac lemma. So for Massac lemma, it is on a finite set. So let's A be a finite set, A1, A2, A, N in Rm, okay? And we define as 1 over n sum n of Ai. And then we managed to prove that the mathematical complexity of A is less equal to maximum of A minus A bar square root of 2 log n divided by n. So we can see that that mathematical is bound by an expression which take in consideration the size of the set that we are taking. Okay, so this work for A, which is finite. And in the proof, actually, we use the union bound in order to prove this, this inequality. But the question here is that what happened? If A is infinite, or A is bigger enough, what will happen? How can we bound the mathematical complexity? That's the question. So, so if A is finite or if A is big enough, we need to use a tool that I might call it as a sophisticated union bound. So that is what covering number will help us to do. It is a sophisticated union bound that will help us to give an upper bound of the dimension complexity of a set A when A is infinite or large enough. Okay. So actually that is the motivation behind that. And the idea here is that we're going to discretize A because A is finite. So we're going to find another set, maybe A tilde, that is a subset of our set A, which is infinite. So we are discretizing our set A to a finite subset A tilde. And then with that now, bounding that A tilde will help us to bound the set A. That the idea. So the process of discretizing that set A tilde is what we're going to use a covering number in such a way that for every element in A, there exists a neighborhood, a closed neighborhood in L tilde. With closed neighborhoods, so that the distance between that set, we're going to find every element here has a close element in L tilde. Okay. Okay, that is the motivation so far. Okay. And we start now with defining what I call covering number. So first, let's A row be a matrix space. Rho is actually my distance. Okay. Now we, if we fix R, we can define a ball with radius R, centered by A. So B R A is the set of A prime such that rho A prime is less equal to R. This is called the ball. Radius R and center R at A. Okay, so we call an R cover of my set A and a R cover definition with respect to my norm, my distance. With respect to O is a finite subset. Is a finite subset that I denote C. So it's a finite subset C, which contain the elements C1 to Cm. So C here is a subset of our original set A. And in such a way that A is a super subset of the union of all those balls. In such a way that this A here is a subset of the union M of all the ball center at C with radius R. Okay. Okay, maybe I can write instead of write AM center as at AI with radius R. That's what we call that a set is called R cover. What does it mean? Simply, it means that for every element A in capital A, our original set, there exists A prime in our set C, which is our cover, such that the norm between A and A prime is less equal to R. And we say that C R cover, yes.
Is n the minimum number of such points?
No. So I'm going to define now the minimum number. So this is just any set that R cover. That's a good question. So now we can define the minimum number as n. Okay, n. But how do we denote it? Yeah, R A with respect to the distant row. This one is I'm calling the minimum of the number of elements in my set C, such that the set A1 to AM, which is a subset of A, is a subset of the union of all those balls center at AI I to M. Yes. So we denote it like this. So it's the cardinal of the smallest C, capital C, that R cover R. Okay. So let me illustrate what I'm saying. So suppose now that I have my A is a circle. My A is a circle. So just a graphic illustration of what I'm saying by a couple. So I will take the element A1 up to AM here to be inside my circle, which is this circle is what I call my A. Okay, so what I'm trying to find out is that, okay, I say that all those elements are cover C A if actually all those balls center at A with radius R are subsets of A. So let me I'm drawing all this the ball. Okay. In such a way that the distance, the radius of all those balls should be less equal to R always. Okay. All right. So we say that all those points here are R over A. That's the graphic illustration. Okay, so there is another notion but it's not in the book. Another number that we call packing number, but maybe it's another thing. But actually, those two are related. Yes. So okay. So for packing number, they want all those balls to not be intersecting in such a way that if I have a set A, all my points will be inside the circle, but I can find a ball of radius r such that all those balls are not intersecting. So we say that those elements are packing number of A. Okay, so let's give an example of this expression. So actually, what we are looking for is this expression that we are looking for. Remember that here in my master lemma, I start with a finite set. So if A is infinite now, I will be able to discretize A to a finite subset of A, which is my R cover, and I will take the minimal of them. So I'm taking now the minimal of them, of all those R cover, and taking the size. So you see now that actually where we need to work on is find the bound on this number, because we have in our master lemma this area which was the size of A. Yeah, so that's the idea. So we're going to find out what is the bound of the minimal number of cover. Okay, so let's give an example. So let's okay, so let's see the maximum. Okay. So actually, we assume that my A, which is subset of R, is a subspace of dimension D of Rm. Okay, so A is a subspace with dimension D. So we can assume that we denote V1 as the orthonormal basis for A. Okay. So then every element in A, since it's a basis, can be written as a linear combination of those vector in basis. There exists some alpha I such that A can be written as the sum of VI alpha I 1 up to R. Okay. Now, those alpha I here are the coefficient. Of T. So when we take the infinite norm of all those coefficients is actually less equal to a norm 2 of alpha is square. Yes. We're taking the maximum of all of them, and we are taking the sum, the square of all of them. So this will be less equal. So you have the relation between the infinite term and the norm 2. And this alpha I here is the same as the norm of A. Yes, the same as the norm of A, because I'm assuming that by definition, the norm of A is just the square root of the alpha 1 square square. Since this is the basis, so this, the norm of this is equal to the norm of A. Yeah. Okay. And actually, the norm of A is less equal to C, which is the maximum. Okay, that's one relation. We're going to use that relation in getting, okay, this example, what I'm looking for is we try to find the upper bound on the upper bound on that number. Okay. So now we're going to define or discretize my set A prime. So how am I going to do that? This is how I'm going to discretize my set, because my set A is the set of all linear combination of V1 up to Vp, and of course, my set A prime is also a subset of A, which will be also the linear combination of V1 up to Vt. But I will try to discretize my coefficient alpha I. How am I going to represent those alpha I? So I assume that my alpha I will start with C, with this number, okay, minus C, okay, and I will end up with C, and I will do the such way that the distance, the step, my step will be epsilon. So let's epsilon be in R. So here, the second point will be minus C plus epsilon, and minus C plus 2 epsilon. So this is how I'm discretize. So the step here is epsilon. That means that the discretization, we have actually 2 C over epsilon points after discretizing. Okay, so then I can define, see this part? Yeah.
It's okay, you can keep going, yes.
Okay, so now, okay. My A prime, which is a subset of A, is also the set of linear combination of V1, so it is sum of Vi alpha prime I over D for all alpha prime I actually are in those points here. So here you have A0, A1, A2 to A2 C over epsilon, something like that. So A2 C over epsilon. This is how I'm defining A prime. And after defining this, actually my claim is that A prime R over A. That's my claim. So let's prove why A prime, this set, which is a discrete, and this set actually is a finite set. Okay, first of all, the finite set. let evaluate the size of A prime is we have a total 2c over epsilon to the power d element. Right? Because the number of points here are 2c over epsilon, and we take those coefficients d times, so it's just 2c over epsilon d. Okay, which is a finite set, which is what we are looking for. Is a finite set.
Please can you explain more about the coefficients alpha is prime?
Yes.
Can you go ahead?
Okay, so first of all,
And also alpha I is a scalar.
yes. Okay. All right. So Rm is a vector space. So this is subspace. So R here is a subspace. So it's subspace over R. So my alpha I here are in R.
Yeah. Okay.
Yes. Okay. So here, and actually this subspace, I think is infinite there. It contains infinite element, right?
Yeah.
It contains infinite element. So what I'm trying to do here, I want to find another set which is finite that can cover A. And for sure, since this set here should be a subset of A, maybe a subspace structure of A, so it has to have a basis as the initial basis, D1 to BD. So any element of my A prime will be written as the linear combination of alpha VI, alpha I, doesn't matter actually. A linear combination of the basis. But those alpha I here is what I'm discretizing in such a way that I will get a finite number of vectors in my set A prime. So the way that I'm choosing my alpha prime A, which is not any random element, is my alpha prime A. I took the alpha prime I as those points. So I'm considering an interval of minus C to C, and I'm discretizing into 2C over epsilon. So each alpha I here will take either minus C or minus C plus epsilon here, or minus C plus 2 epsilon, or minus C plus 3 or 4 epsilon. Yeah. Did I answer your question? Did I answer the question?
Yeah.
Okay. Okay. So this is how I'm constructing my A prime, which is subset of. And it's yes. The way that I'm doing it is finite, and I can count the number of elements in A prime, which is 2C over epsilon D, which is what I'm looking for actually. Yes. Okay. So okay. So what I'm doing.
And how do you choose the step?
The step. My step is I let epsilon to be my step.
You can choose it.
Now later, yes, I think that's a good question. So actually, because I want to prove that A prime R over A. So I will choose in particular epsilon to be R to the power R divided by square root of T. I will choose that. But the way that why I'm choosing this, you see it in the proof. That okay, this epsilon has to be in a way that okay, we have actually R covering. Okay. So A claim is that A R cover A. What does it mean? So by definition, for every element in A, there is this A prime in C such that the distance is less than R. So that means that let A be A. Okay, every element in A has to be written as this, okay? And so alpha I, okay, so yes. Then there is this A prime, in A prime such that we're going to compute now the distance or the norm between A and A prime. Okay, that norm. So this is just the sum of AI is alpha I, BI 1 or 2 T minus A prime, which is a sum 1 T alpha prime I. Okay, so this I can factorize those coefficients. So we get sum alpha I minus alpha prime I up to T. Okay. Okay, so this this term here. Oh, okay. Actually, let me take the square. Let me take the square. So I'm taking the square. I'm taking the square. Okay. Okay, so taking the square, I'm evaluating this norm and the distance. So this actually will be less equal to the norm of and remember that my VI here are unit vector, autonomous basis are unit vector. So that means that the norm is 1, and taking the summation of those unit vector 1, 1, 1, d time is d. And the distance actually here is alpha. And okay, I can actually use a square because I'm taking the square of all those. Square. So this is equal to epsilon square t. Okay, so I managed to prove that norm of A minus A prime is less equal to epsilon square t. So I choose epsilon here to be r divided by the square root of d. If you choose that, then we have A minus A prime less equal to r. Yes. No. Yes, this is square. Okay. So we managed to prove that A prime r over A. Okay. And actually, remember that I wanted to find out what is this quantity, the minimal of all those r over set. So N of RA here should be less equal to A prime. Right. Because it's the minimum, it's less equal to the size of A prime. And we already evaluated the size of A prime, which is 2c over epsilon to power d. Okay, so that's all. So then we can just replace that epsilon by r over square root of d, and then we get that this is 2 c square root of d over r over d. So my n is less equal to this bounded value. For this example. Okay. So we'll see later, after maybe getting the upper bound of the random complexity, that when we are dealing with this, since we bound this number, and actually our discretization is A prime, we just bound this number to this here in the logarithmic of, actually we are looking for the bound of the logarithmic of N RA. That's what we are looking for. And then we just replace here, and then we get a tight bound on the mathematical complexity of A. Okay, so that's one example. The example and question. Epsilon squared D. Okay, so
This one is one.
huh?
This one is one.
Yes. Yes.
Why epsilon alpha I minus alpha I prime square is less than epsilon square?
Is less than that because of the way that I'm choosing actually my alpha and alpha prime. I'm choosing them in a such a way that they are distance of epsilon. This is by construction. By construction, those alpha prime here that you see are actually look the concept of discretizing or R-covering is that we are from our set A, we are looking for a subset of A prime, a subset of A, so that every element here has a close point in A prime. You see, every element here has a close point in A prime. And the way to assess that closeness is to take the distance between alpha and alpha prime to be epsilon. My epsilon, which is the dissertation. I think epsilon here is very small. This really explains that, okay, every element that I'm getting here, that is a specialized linear combination, has a neighborhood in A prime, which is very close. Okay. If I don't know if I answer the question, but you're not convinced, eh? You're not convinced, but okay.
So can I just say, can he ask more precisely where is the problem?
Like,
Yes.
I'm asking if why this alpha I minus alpha I prime is always less than epsilon.
No. Actually, alpha I minus alpha prime is equal to epsilon.
It's equal to epsilon.
No, it's at most epsilon. Okay, so I think for this the explanation you have in the picture, which is in the bottom. Yeah, so that's how he defined it. He said, let's take into A prime all the points from minus C, the points from minus C to C, and then just take like a discrete grid of the step epsilon. Yeah, so you take minus C, then you take minus C plus epsilon plus 2 epsilon, and so on like that until you reach C. Which means that now whenever you have some alpha I, so just some point in your big set A, you are guaranteed by assumption that this point has a coordinate between minus C and C. So it's somewhere on this line. And if you have this line and you have this grid of points of distance epsilon to each other, wherever you put the point between minus C and C, there will exist some alpha prime, which is at the distance at most epsilon to you. Yeah, just because you put the points every epsilon, so you will always find, wherever you put some a point, you will always find one of these discrete points at the distance at most epsilon. Actually, it's even epsilon over 2, but like that's just just a constant factor improvement.
Okay. Thank you.
Good. Clear? All right. Okay, so what we're going to do next is okay, so we're going to give some basic property of that number. Remember, I could say the most important thing here for this chapter is looking into this number. That's why I will know. Okay, that number. So basic property about this number. So one property. If I take any subset of Rm and a scalar C, which is equal to 0, positive, A0. You remember also when we were giving some property about the Random complexity, scale a set by scaling and translating the element of a set. When we evaluate the random complexity of that set, is less equal to the constant, the absolute value of C multiplied by the random probability. So here, for every R greater than 0, that number R, this set, CA plus A0, so that A element of R is less equal to N of CRA. Okay. So I can just give the proof from the definition. I can give the idea of the proof. So here, look, we can say let B, and I choose B to be a set CA plus N0 A element of A. Okay. So all right. If I suppose now that my A prime, actually, yes. Here we have CR. Okay, if I let A prime that CR cover A. So let A prime actually be the minimal that CR cover that simply means that my size of the size of A prime is actually N CR. That's what I mean by this. And I want to show that my A prime here C cover B. That's it. So if I manage to prove that my A prime C cover B, then N of C of B should be less equal to the size of A prime, and then we are done. Okay, so how to prove that A prime C cover B? Let's okay. Let B be an element of capital B. That simply means that there exists A in A, such that my B can be expressed as a CA plus A0. Okay. Now, so okay. So what I'm going to do here is that from this, we already assume at the beginning that A prime is the minimal set that C over this. So I can just use this by from this simply imply that there exists for every A in A, there exists A prime such that the norm of A M prime is less equal to CR. That's the implication. And remember that the C is a positive number. So then I can just divide them by C. Okay? And what do I have now? Okay. Okay. So actually, I want to evaluate the distance between B and A prime. That's what I want. So I can re-express as A, C, or CA plus A0 plus A over C minus A prime over C minus AC minus A0, which is less equal to R. So this thing here is my B. Right? Yeah, it is my B. Okay. So I think the existence of an element A prime that we are looking for, we could take it as this. So maybe I think we also need to see that okay, this element here is the A prime. Then we are done with the proof. Because what we know, proving that A prime C cover B is does mean that what we wanted to prove is that let A B factor B. So there is this maybe A prime, let's say T A prime such that the norm of B minus T is less equal to R. So using this, I get into this T, we can choose the T as this number and show that the T is it's not C. It's C or R. No, here is R. And this is T.
You want to show that A prime C cover B.
C cover.
Like the difference between two, you have to be less than C or R.
Okay, C. Also, I think it's R cover. Yes, it's R cover. Thank you. It's R cover. Yeah, it's R cover. That's what I want. Okay. Okay. That's one property. And another property is about the contraction principle that we also see in the previous chapter. Lemma 2. Okay, so let's consider rho Lipschitz function. 5. Let R from R to R actually be rho function. So we all know what does it mean, okay? That the function is rho Lipschitz, okay? You want me to recall to you?
A0 beyond this.
A0 here is a constant. Okay, so my taking A in Rm, my find A here 1 by phi A to be phi 1 of A1 to phi M of AM. Okay, so I want to evaluate the image of for my set A by my relative function, which is phi A. Okay, and by definition, this is just phi A or A in. Okay, and the question here is that how can we express the that number n? What is the n of phi A? Okay, and actually they prove that n rho r is less equal to this. They prove that. Okay. This is just a basic property. Okay. So the idea of the proof so if let's define actually B if I take B as my phi A. And I suppose that A prime R cover A. Okay, so suppose that my A prime R cover A. So actually, we define B prime to be the phi of this cover, the phi of the image by the little function of my cover A prime. So what I'm trying to prove here is that okay, this B prime rho A cover this. That's all. This okay, claim. I want to show that B prime rho R cover my phi of A prime. So if I manage to prove that, then we get the result. Okay. Okay. So let's do it. So, but remember that we assume from the beginning that A prime R over A. So that simply means that there exists for every element in A, there exists A prime such in A prime such that the norm of A prime is less equal to R. So proving this, B prime rho R rho over A prime simply means that we need to take an element phi of A, evaluate the norm between phi A and phi A prime, evaluate this norm, and see that the norm is less equal to rho R. Okay, and actually we take the square. Okay, so this is equal to, by definition of the norm, is just the summation I of phi A phi A prime square. Yes. Yes. Okay. Okay, so that's what I'm showing you. By definition of norm. Okay. So we from the property of primitive function, this phi IA is less equal to rho I, and this also less equal to rho A prime. So we're going to get this less equal to rho square of sum of I minus AI prime square. And from the assumption, we know that this is less equal to R, so we can just replace here, and then we get R squared, which is what we wanted to show. So finally, we prove that B prime rho R cover B. And then we are done. Okay, other question? Okay, so now we step into the most important part of the talk. So remember, I still have my master lemma there. That we try to give upper bound dimensional complexity. That's the idea. And from the perspective of, okay, this set A could be an infinite set. Okay, so we have, actually, the principle of chaining, that's what I was explaining earlier. By giving the motivation of the covering number. That's what I was explaining earlier about the principle of chaining. That if A is a infinite, that Mansard lemma is no longer useful. It's no longer useful. So we're going to find or discretize a finite subset of A prime, so that every element in A has a close neighborhood in A prime. And then, given an upper bound on that set A prime implied is the same as given the upper bound on our original set A. And in the example, you see how we start from this an infinite set, which is a subset of a subspace of dimension D, and we discretize to a subspace to another set which has a finite element. Okay, so this theorem here let A. So here now I assume A, and I don't say anything about A. It will be finite or infinite, which it's so it is maybe an improvement of the result of Mansard lemma using covering number. So let A be a subset of Rn. Okay. And let C be. Actually, C here is the minimizer respect to A bar of the maximum of the norm. Okay. So then, for any integer m, greater than 0, is integer. The dimensional complexity of A is less equal to this quantity. C2 to power minus M over square root of M plus C6C over M. So we wanted to factor M to the power minus A square root of log of N C2 minus KA. Okay. So actually, in the literature, they usually refer to the log of this set as the metric entropy. Because you realize that is where we want to find the bound of this. Okay, so that's the result that I want to prove now. Which is, you can see the master lemma and we see the new result, the changing result, and you see that, okay, we see the same. I will root the same, that just a slight modification. And maybe in the last example, we see that, okay, that bound is a very tight bound. Okay, so if you remember how we prove this in the master lemma, we assume A bar to be 0 because of the generating. So here also we assume that A bar is 0 because of generating, and we analyze our random complexity on A, assuming that A is 0, A bar is 0, and actually the proof goes the same even if it is not equal to 0. Okay, so I think about because of linearity that A bar is equal to 0. And here, what we are looking for here now is that we want to discretize my set A to a finite subset of A, which somehow cover A. So for this, we're going to construct some sets, B0, B1, up to Bn. So that's the process of the construction. And those sets, turn out that those sets will cover my set A. And from there, we try to find the random accomplishment on those sets. So let's first of all consider our set B0. My set B0 here is a set that contains 0 elements. And obviously, it's just C. C cover, that's clear. Because we assume that A by 0. That simply means that if you take a distance between A to 0 is less equal to C actually. Less equal to C. Like the norm of A to any element of B0 here, which is 0, is less equal to C. My C is a maximum of. So B0, which is the C cover A. And now let's take our BK here is be the minimal subset of A that C 2 minus k over okay. So not only that my bk is a c 2 minus k over a, but I'm choosing as the minimum of them. It's just a minimum. Yeah. For k, for every k. Okay. So remember here, what we need to pay attention to is we want to upper bound this. So that means that we need to look at the supremum of rho A. Okay. What is the maximum of this quantity? So we choose let A star be the maximum of this quantity, because this is actually is a inner product, which is a function can be expressed as sigma and A, and maximizing over A, which assume that okay, my A star here is the maximum. That simply means that okay, whenever I'm dealing with this, I could just write that okay, the random function A is a 1 over m sigma A of sigma of the inner product of A, the inner product of sigma and A star. Okay. Just take one of those maximum. Maybe there's this min maximum or different. We take one of those maximum. Or even if the maximum does not exist, we take R as that to be an element that is close to that maximum. Okay. So now the element in this set here, I will denote them as BK, which tend to be the neighborhood of A star, the nearest neighborhood of A star. Because you say that BK is the minimum, that means that okay, for every A in A there exists, which is A star, the distance between A, BK, and A star is small. It's small, is less equal to C 2 power minus K. Okay, so what this is saying is just that okay, by definition, by construction, taking this and the element of BK are expressed by BK, B to the power K, and is close neighborhood of A star. That can be expressed by this this inequality. And then we can now evaluate the distance between so what is the distance of BK minus BK minus 1? That's what we want to evaluate to. So actually, we can just interpose a prime in between, and this will be less equal to A. So since we assume that A star is the maximum of them, every BK is close neighborhoods. For K, 1 of M is close neighborhood of A star. All of them, they are close to A star. Okay, so if I interpose, like here we get A star minus A star. And by the property of the closeness, the nearest closeness part, this actually is less equal to C2 minus K, and here is C2 minus K minus 1. Something like that. So it's less equal. So we can factorize by C2 minus K, and then we add them and we get less equal to 3C2 minus K. Okay, so yes. Rho. What is that? Inner product. Sigma, what is sigma? From the definition, okay. From the definition. Remember our definition of the domain complexity before? We choose. Okay. This sigma is a new random variable that we are introducing in our random function definition. And actually, it takes value in 1, 1. Okay. Yes. It's clear. Okay. So it's those sigma that we are using until now. Just the cover number is just a continuity of the data flow. This one. Okay. So what I'm saying here is that I'm assuming that BK here. So maybe I can write my BK as those sets. Is a set of okay, those elements, okay, and all those elements are close neighborhood of every element. Maybe the other. If I take any element in A, I will find a close neighborhood in B, which can be at the top. But especially when I'm taking the maximum of all those, which is A star. A star is the maximum. Okay, so this maximum will be close to a nearest neighborhood in BK. And that closeness, nearest closeness, is what I mean by this. Remember, whenever I say C cover, remember if I say C cover, A prime, C cover, A prime, that's mean for every A in A, there is this A prime, so that the distance between A prime is less equal to C. So that's what I'm writing here.
But here you have, okay, this is for only this PK, or for because
this is work for every K, actually. For every K. For every K.
Yeah, this is true for every K, just because A star is one of the elements of A. So by definition of the fact that BK is the covering, there must exist an element of the BK at most at this distance to A star.
But after I say that, like the distance between
Here.
B K minus 1 and A star,
Yes,
is less than C
K.
and 2 to the power K minus 1.
Yes. You see, now look at this BK here, the covering, the coefficient here is a function of K. Here. So if you see now this BK minus 1 here is just a closed neighborhood of an element of A star, which is in A. And that close neighborhood here, the distance between them should be less equal to C2k minus 1 because of the
So we have many this type of BK.
okay.
Addition. This BK
Right. Right. Here. Oh, okay. So right in there exists BK. Something like that, right? Such that we have this. Okay, okay, it's clear. But you are saying how to generate those BK.
We just use the function.
So if I understand
Yeah.
correctly,
Yeah.
this BK and BK minus 1 does not belong to the same set.
Does not belong to the same. Actually, okay. So those are two different sets. Then, if I'm okay, like I'm having B0, B1, to BK minus 1, BK, to BM. Those are.
I think this one B does not belong to the same set.
This
Like
one,
BK
BK minus 1
and B.
BK minus 1 belong to this set,
Okay.
and BK belong to here.
Okay.
And this always exists.
Esta,
The
the BK.
always exists.
I think it's how does it exist?
It always exists.
By construction, right? By construction, yes, but by the construction. The way that I'm constructing, I'm choosing my BK to be just the minimal subsets that's here about. So that means the system. Okay. I can continue. Okay, so that's where I stopped. So I managed to just bound this. So why am I bounding this? We'll see later why I'm doing this. See why this is needed. Okay, now let's what we are dealing with is this. So 1 over M. So what I'm going to do now is that I'm going to introduce in this expression, this expression, I'm going to I will subtract dm and add dm to this. Okay, I didn't do anything. Yes, I'm just adding exercise. And actually, it's because here, if I'm taking the summation of K1 to M of BK minus BK minus 1 here. Actually, this will give me B0. I think plus BM or something like that. Because it will cancel out. Okay, so that's what I want to use here. Okay, so my BM here will be okay. First of all, I can split. I can split this. So this is 1 over M. the expectation. Okay, of sigma star. Maybe I just going to yes, minus df. Okay, sigma m plus b0. B0 here is 0. 0. Okay, so this is what I get. Because of the super thing that I'm doing. Yes. So that's it. Yes. Okay, let's equal. Okay, so actually this part here, the supremum of this, remember, I already take A star as my maximum of those. So I can just take the star as the maximum and remove the supremum. Okay. Good. And here, remember that summation that I wrote, that summation that I evaluate is just give me this. And B0 here by the definition, B0 is 0. So I will get 1 over m star minus bm so that will be the summation of k1 up to m, k from 1 to m. So we have a summation k1 up to m of sigma b k minus bk minus 1. Is this here? Okay, that inequality that I wrote there. I just use the decomposition of BM. Okay, good. So that's all. I can just continue here. Okay, so this is less equal to the size, so this is 1 over m. And this is less equal to the size of because we are taking any product, the size of the norm of A multiplied by the norm of this, and the norm of sigma is m. The norm of sigma, the norm of delta minus dm. Summation k1 up to m 1 over m. Okay, so now looking at this, I'm going to define a set. I stop here, and I reach to that point. So I will define. Let's define another set that we call BK bar. which is the set of A minus A prime for every A in BK, A prime in BK minus 1. In such a way that the norm between A and A prime is bounded by 3 say 2K. So that's the new set that I'm defining. So here we want the supremum. So taking the supremum of this quantity is just taking the supremum of sigma A, where A belongs to that set. That's a B. Here, the supremum. I'm getting the supremum over this one. This is like what? Look. Yes. So this is a set of elements. So my supremum here is over the set of all this. So maybe how can I write it here now? Is the supremum over BK minus 1 or something like that.
Because if for K, for the fixed K, we have the fixed BK and the fixed BK as well. Maybe
What?
for K maybe equal to 1. We have just the sigma of
Is B1
B1 minus
B0
and O,
which is the set,
and 1.
which is
What does this one mean with this kind of expression?
okay, to better view it, that's how I define this. You see this set B bar K is a set of A minus A prime, so that A belongs to BK and A prime belongs to BK minus 1. So all those elements that you are saying here are in this set, in the set BK, B bar K. So if you take any element in BK, it will be expressed as BK minus 1, which is what we are doing here, which is the rewriting of that supremum. That I'm taking A for taking the supremum over A where A belongs to BK.
So here, one of the
Okay.
say that there exists BK in this BK. So here BK is fixed.
The small or capital?
The small one, the element in the capital.
Yeah.
It's fixed.
Yes.
And now here we are proof for A. And we are talking for a fixed BK. If you want to consider the supremum of the BK.
The first line when you introduce BN, you mean
Here.
you mean for any BN, right?
Yes.
So effectiveness is for any BK.
So I think how it goes is that like all these things are functions of sigma. This is maybe not indicated in the notation, but because first of all you have A star, and A star is the one that maximizes this scalar product sigma and A over all elements in A. Okay, so A star itself is depends on sigma. Yeah, it's not constant throughout the whole expectation. It's a function of sigma. And then each BK is just the nearest element to A star in the covering. So BKs, all these things, A stars and BK, A star and BKs, they are functions of sigma.
Right, in this case.
Yes.
The problem is this line,
This line.
this line to the last line, yeah.
Yes.
Like this part.
From here to here.
Yeah, I mean this part, only this part.
And the problem is the supremum part.
Yeah, this is coming one.
And okay, this is
First, we can
okay.
Can we remove this first scroll over?
This one supreme.
Since this part does not depend on A.
Okay, so let me do this. What you say?
I don't get this because the solution was good because like it was telescopic sum, but now you add the supremum. I don't get it.
The supremum was still there.
But he says that there is no A inside the schema.
Ah, that's the problem. Okay. Let's do this. See. Okay, so originally, that's what we are dealing with originally. For A in A, okay? So, and actually, the problem that we are dealing with is a function of sigma. So sigma also with yes, okay. The A star sigma also is an expression where we need to find also the supremum. Okay. Maybe I'm not getting your point, but okay. So I think here, in order to write correctly on which element I'm getting this supremum, that's what I'm dealing here with this. That's even here. Here.
First, the first line is good. The second,
this line is good.
like if you put
this one is good.
This one is good.
Okay.
Now this one,
yeah,
you can put over A, soup over A.
Soup over A.
But
here,
yeah, because it's just inequality. Okay. Now from here to here. First, I realize that this product, this inner product does not depend on A. Is it correct? This inner product.
This inner product here.
So I think like you can eliminate the supremum from the notation one step before, okay? Because just the definition of A star. A star is the A in A that realizes the supremum, okay?
Yes.
So the expectation that you have in the first line, you can write it also expectation over sigma. You know, the scalar product of sigma and A star minus BK plus BK, blah, 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 okay? But it's just a notation, like these things still depend on the sigma and you just choose the one that is that realizes the supremum.
Yes. You see what Jan was saying? So there's no need to write this, right? Okay. I guess.
No, it's good. He's just saying that you can remove.
Yes. All right. Like this,
Plus. I said he said you can remove this this from even in the first line by putting it just this line.
No, in the first line is correct.
Yeah. So
putting A star up there.
Here. A star here. And still keep
and remove the supremum.
Okay.
Yeah, like it's not false, but maybe it's misleading because this BK and BK minus 1, they depend on A star. So somehow it's like not good. Yeah, I think that's better. I agree.
Yes, okay.
Okay, but is there any supremum in the last line?
No, I don't think so.
Okay. Okay. But so if you remove this,
Or okay, so the supremum in the last line, Prudence. This
Yes.
for this you need to, did you introduce this set like this BK hat or something?
Yes, yes, that's the new set that I'm introducing, B bar K.
Because the last line for me is like a telescopic sum, so like this is good.
Yes.
But now from here to up there, I don't get it.
So, okay, so my understanding is that if we keep the supremum and knowing that this quantity that we are stating, we still need to evaluate the supremum on each side, depending on the other part of my inner product. And getting here, now I'm taking the set of all those elements. I'm consulting a set that contain BK and BK minus 1, which I wrote it here. So evaluating the supremum over this is just taking the supremum over sigma A for every A in BK. But if I understand you correctly, that since we do not have supremum here, why we should keep this?
I don't just
That's your comment, right?
no, my comment is just like I don't understand why.
You don't understand
This part, yeah.
this part. But it's just this set. Okay, do you get that set? That new set that I'm talking about. This set. A prime, A minus A prime for A in BK and A prime in BK minus 1. So any element of this set is at the form BK. Any element of this set. Such that they are bounded by this. Okay? So, yeah.
I'm not confused. The BK, BN, they depend on A star or not? Or it's A?
Actually,
PK depends on the star depends on C.
The small BK depends on A star, yeah, because it's just the closest element to A star from the covering.
yes, yes, yes.
In that case, I think like Donat that there is no supremum.
So I am not seeing what is written on the right of the blackboard, right? But, so you do it. You have two steps. The first one is just you use the linearity of expectation. Okay.
Are you able to see now?
It's okay. Yeah.
Okay.
And then you make this, and I mean this is somehow the place where you eliminate this infinity. You see. So now you observe that over all possible that. You know what you have in the line at the bottom, BK minus 1.
Mm-hmm.
It's a vector. It's some vector, and in general it depends on sigma and on A star, but it's coming from a finite set, right? And this finite set it's just a difference of something which is in the big BK and something which is in the big BK minus 1, and these two are now finite sets, yeah. And like even not just finite, but we can bound their sizes. And that's why this set BK with the bar is defined, right? It's just the set of all possible differences where one element is from the big BK and the other element is from the big BK minus 1. And then on top of that, also what you also know always that the distance between the small BK and small BK minus 1 is at most this bound that you had, this C 2 to the minus K, yeah. So additionally, you can also like add this constraint. So instead of the scalar product that you have on the bottom, small BK minus 1, you can take the supremum over this set big BK bar, and yeah, you can only increase your value, right? So you can bound it by supremum over this finite set. And now you eliminate the dependency because now you are just taking a supremum over some big finite set, but you don't worry anymore that it depends on sigma and all that.
Really? Okay, thank you. Okay, thank you. Right. The conclusion is that that's what it's supposed to be. No,
Yeah, it's a hard proof. Like,
yes, yes. Huh?
We are just bounding this. We are finding an upper bound to this one, BK minus BK minus.
Yes.
And we still have this summation.
Yeah, the summation is there. The summation is not affect anything.
Okay.
The summation is there.
Okay.
Hmm?
Okay, because we have this BK.
Okay. All right. Shall we continue? Okay, great. Okay. We want to have maybe.
yeah, sure, of course.
Okay. Okay. So. It's impressive. Okay, so that's it. Yes,
But he doesn't see what it is.
You want it to be completed or learning is like it's not easy.
If the channel is without feedback, what we did is this guy and to scan this.
Because they are using so I'm trying to make it
Using reversible. No, but we're still using the reversible thing.
Yes.
Yeah, that is
I'm talking about using face-to-face. And if it's using using the regulate. Yes, but we got if I'm going with this that's
I'll just explain you what I tried.
okay. Yeah, that's right. Yes.
And yeah, so one is it's frustrating. I tried something we wanted to use the data set C4, and then I was trying to run the code,
This channel, particularly
looking at the HTML.
C'est ça, alors, il est
Yeah, and I added more things, and then it worked. So
Et ça aussi.
it looked like I could
Je pense que ici,
Comme-
je suis en train de montrer le cas. J'ai une symbole qui va
I could convert it, but then when you convert it,
parler d'un cas général.
you convert it into the
Et le input n'était pas un output.
TXT file format,
Ok.
and then you want to work on this file, but then I still got
Yeah.
some error on the index frame.
Est-ce que si j'avais liste ici, ça va je donner
I'm
liste.
sure you
Si tu dis déjà que
So-
liste,
that means I
en
could
fait, il y a des
still
liste.
find like simpler example
Ça, c'est pour
than
liste.
simple. Then
Normalement, c'est ça. Il me fait un petit peu ça. Est-ce que ça peut être ça? Non, juste ça. Ça, expliquer ça.
Okay, so I want to resume. So we are still. Can you hear me?
Yes, I can hear you. It's all good.
So we are still in the process of the proof, and we were in the middle, and we stopped somewhere there. So let's continue. Okay, so we managed to get a bound here. So, okay, that sigma, the norm of sigma is just square root of m. Because remember when we take the sigma, they are -1, 1. So we take 1 to square minus 1 square, m times, it's just m. So it's square root of m. Sigma is m. And if you remember what I was writing here, that every element in BK is a close nearest neighborhood of A star. That simply means that the norm of BK minus A star equal to C minus K. And in particular, that K is from 0 up to M. So if I choose K to be M, then we have norm by C2 minus M. Yes. Okay. So that's a first. It's first because we're going to use that in the inequality now. And okay, so let's look at the other part. This part.
Prudence, I think norm of sigma is square root of n, or norm squared is n. Yeah.
The square root of m. Yes.
Yeah.
Yeah, it's square root of 1 square times, so it's square root of m. Okay, so if you look carefully, this quantity here, this one is just that we're trying to evaluate the random marginal complexity. I think that we are evaluating the random marginal complexity of this set DK. Right. So I was looking to the master lemma. That's where I stopped. And actually, yes. All right. Because that set BK bar here, that set BK bar is finite, then I can do to write this, and that norm A here is the norm of A minus A prime. Okay, so just some notation issue. Whenever I'm writing A here, A here denote that A is in B bar. But this will be less equal to, okay, let me say this part, the last part, which is the 1 over m of the expectation over sigma of the supremum of sigma A. Which is actually what I think is the same thing, but so this now will be less equal to the norm of A minus A prime multiplied by square root of 2 log size of B bar over M. Okay? But just be careful here. This A here is not the same as this. When I'm writing this A here is just that I'm thinking as in BK. Hmm? Decent. Yeah, it's going to be confusing. So, but you just need to know that, okay, actually what I'm saying is that this A here is in BK and A prime is in BK minus 1. So this distance is, I will already show that it is 3C2 minus K. And actually, remember that my BK here, as what I said at the beginning, that BK here is the minimal C2 minus K cover of A. The minimal C2 minus K cover of A. So that simply means it's just this. But by definition, this is just the minimum of the cover of size. So this is 2. So the size of BK is 2 log n of C 2 minus K A. That's what it means. Divided by M. Oh, that's where we reach. Okay, so now I can combine. I just bound. You see, I bound this by this quantity, and this is bounded by the quantity square root of m over 2cm. So combine the two together. Against that the Rwanda complexity is less equal to square root of m divided by c is 1 over m multiplied by square root of m multiplied by c to the power minus m. Okay, and the other part is just this quantity plus 3c minus k log of n c 2 minus k a divided by m. That's what we are looking for. That's the bound. We try to find out the bound and in function of the metric entropy, which is in function of the covering numbers. Okay, so just one more lemma. So if I assume that there exists an alpha vector actually, such that remember in the previous example that I gave, for when I give the definition, I give an example, and then we bound actually this quantity nr reach that bound. Yeah, record here somewhere. Let's say here it's bounded by 2c square root of d. Square root of d over r to the power d. That's what we get before. So getting this, I can just take the logarithmic. If I take the logarithmic, which is the metric entropy, then I could rewrite the bound on R on the logarithmic over A. So this lemma, it will help us to get another expression of the bound by just assuming that, okay, taking the delta, if that logarithmic has a special form, like if there exists alpha and beta superior to 0, and for every k equal to 1, if that expression, that 2 log of n c2 minus k is equal to alpha plus beta k, then A is bounded by 6a over n alpha plus 2 beta. Solution. Which summation? Yes. Yes. Okay. Thank you. There is a summation here. There is summation.
And here you still have to put max between in front of this norm of A minus A prime.
What did you say? So
I know it's not important. I sit down there. With max there, but it's not important.
yeah,
Not max. Because here, A will go more there. What's the
but it's work, right?
We have to put max. I think. Max. Because we. But then we bound
Okay, but if I put the max here.
over here. That's good.
Yeah. But remember, okay, so also that maximum will be bounded by this quantity. All right, so it's clear. So here, what I'm going to do here is we just use this expression. It's very easy. We use the previous expression and we evaluate with tends m to go to infinity. If m goes to infinity, you see this will disappear because this quantity, when you evaluate the expression of this, it will be 0. And actually evaluating this expression, when m goes to infinity, you see that you get the sum of series. The sum of series. And that summation for k1 up to m of 2 minus go to infinite of 2 minus k is going to be 1. So then we can simplify and get this expression. So this lemma is just a direct consequence of the previous lemma by just taking m to go to infinity and using some of the series. Okay. And last is the example that we started before, where we reach to this point. Okay. So we remember that that's an example that we take A to be subspace of dimension D of Rm. And we find the upper bound on this. So we can now express the radiation complex over A using those lemma. So first of all, we evaluate the log, we evaluate this quantity. We just use this lemma, and so we have this, we evaluate this quantity, and we see if there exists some alpha beta. So if you get that alpha beta, now we just plug it here and again, then we are done. So that's the example from the beginning that okay, A is the subset of M, such that A is a subspace of dimension where is the maximum A. Okay, so then we're gonna evaluate the square root of log. So just here, what I'm going to do, I will replace my R to be C2 N, C2 minus K, A. Which is the square root of two C square root of D over C to power minus K. Okay, something like that. Okay, the power D. Okay, that's, I just replace it. Okay, and then this is, like I can simplify by this, and this will be 2 K plus 1 square root of D. See how the log, or see how the log. It's log. And this is log. Log of 2K plus 1 square root of D to the power D. Okay. So using the property of the log, this will be less equal to square root of D. D log of 2K plus 1, which is K plus 1 log of 2 plus log of square root of D. Something like that. So yeah, so finally we get so this will be less equal to D log of T plus plus K. And actually, square root of D, square root of K is less equal to K. Okay, so then we have and that is the existence. So this is my alpha, and this is my beta. Okay, so I get the existence of alpha and beta, which are positive. Then I can just plug it in the previous lemma. Plug it in the previous lemma. We have is equal to 6. So M square root of
further deep. The expression of this example.
Okay. So yeah, I think they express in function of big O, just to see that this is just a touch bound. They express it in the big O, they see that it's a touch bound. That's explain the improvements of the relational complexity using the covering number. So that's the end of this chapter. And I noticed that in this chapter they haven't used they have not the example is not so useful from the learning theory, like in the chapter 26, where we evaluate the data complexity and get the general bound of SVM. But
I think it is also sort of, but yeah, they skip it, but you can I think you can work just a little bit to make it an example from learning theory, yeah, because you have this class of vectors, and these vectors are just you know, the evaluations of the functions in the hypothesis class on your data set. So this is giving you a hypothesis class of functions which are linear on a subspace of dimension D, and they have bounded norm by this C. Okay, and it's like, it's actually, I think we've seen before, like we've studied this class before, yeah? Maybe even with Rademacher.
so yeah, that's the end of the talk. Yes. Yeah.
Yeah, thank you very much, Prudence.
Yeah. So, but I don't know if there are still a little of documentation about recovering numbers up there, but there have been little work done on this recovering numbers thing. Yeah, I try to show it, but yeah. So I don't know if there are some recent paper on that covering number and in the learning theory that.
Yeah, so I think the main thing to take away from this is not even this specific application to learning theory, but this idea of covering. So you have a set which is very large, or maybe even infinite, and this idea of covering by this finite net. So sometimes this is also called like epsilon net, okay? Like this sort of covering that everything is in the distance of epsilon to some point in your covering. This is a very useful idea in general, yeah? That whenever you want to prove some bound, and like you are able to prove some bound for like finite set, and now you have a set which is infinite, but you can cover it efficiently, you know, this is somehow a very powerful idea in many contexts.
Yeah.
So the epsilon that you choose will also determine the complexity of your model. Or you can just take it always epsilon.
I think it will depend on your application, you know, like here, for example, you somehow, you see, like you take this like the first proof was like it works for any epsilon, okay, and then you just choose, and even I think here for this last corollary that Prudence showed, you kind of take epsilon going to 0. You just take the limit that goes to 0. But sometimes it's like, yeah, like you make some argument, and depending on the epsilon, the argument gives you a bound, and then you just optimize it, for example, yeah, to minimize like the complexity or whatnot. But it all depends on a specific situation.
Any other questions? No. Okay, I think we stop there.
Okay. Thanks.
Please. Hello. I want to ask some question about the discrete memory channel.
About?
Like discrete memory channel, like your example that you gave me last time.
Okay.
I want to come. Okay, you want to compute the initial information between xn, yn minus 1.
Okay.
Okay. By default, this is going to xn.
Mm-hmm.
Achieve the formula. And we are asking ourselves why is this equal to which of xn? This one.
Yes, we are discussing this, and the answer is no.
The answer is no.
Mm-hmm.
And I still don't get very well how does the discrete memory channel work, because you know that in the discrete memory channel, like if you want to send a string over a discrete memory channel, like each output depends only on the input at that time.
But okay, so
let me write your example in the
okay.
Actually,
Mm-hmm.
this y1 is the output of x1 to the BC.
Yes. Yeah.
The same for y2.
Yeah.
And z1 and z2 are just equality.
Yeah, and you can for this you don't even look at z1, z2. Yeah. Mm-hmm.
Okay.
But you still okay. So the part that is missing, to define the whole probability distribution, you still have to say what is the distribution over x1 and x2.
Okay.
Right? And this distribution does not have to be independent. This is the reason why you don't have equality. The distribution over x1, x2 does not have to be IID. You know, it's like when you take you have a code and you take a random uniform code word, you can have you will have dependencies between the bits. And that is the reason why you can get some information even from y1 about x2. Because x1, x2 are not independent, and then y1 gives you some information about x1, and that gives you some information about x2. Huh?
Okay. So here x1 and x2 are not independent.
Yeah. So the example I gave you, this example, if I remember correctly, then I said, so now let x1 and x2 be always equal, and x1 is just uniform in 0, 1.
Okay. So, okay, if I get it well, that means in this case, each xi has own distribution.
Each xi
has own distribution.
I mean, x1 to xn has its own joint distribution, and this can be a very complicated distribution, right? Which is described by 2 to the n parameters. And now whenever you have such a distribution, you can take, it's called a marginal, right? You can just say, okay, inside this distribution, what is just the distribution of just xn? Or just xn, xn minus 1, and so on.
Okay. But here you can just, since you have yn, you can just remove this one. But this is correct. I think.
I don't think so. I think the other way around would be correct. If you are looking at h of an yn given xn, then you could remove the conditioning. In this case, no, because also you don't know the prior of xn. I think even in the example that I gave you, I think even if you compute this one, the one that you are subtracting, I don't think it will be exactly the same. Yeah, so to convince yourself, just take this example. Remember about the distribution of x1, x2, yeah? So it's just probability x1, x2 is 0, 0 is 1/2, and probability that it is 1, 1 is 1/2. X1 is Bernoulli 1/2, and x2 is equal x1. It's just equal x1.
Okay.
Okay, and just, you know, I think this is like simple enough. Just do the whole calculation and you'll see that like the numbers will not be the same. Yeah.
I will do it. Any question? No. I will do it and let you know after.
Yeah, that sounds good.
Okay, thank you.
Thanks.